A sistemarsi. Come vedete c'è grande affollamento per il dottor Barrow, per il professor Barrow. Come sapete questa conferenza viene tenuta in lingua inglese, quindi chi di voi ha necessità di dotarsi del materiale per poter seguire in traduzione può farlo utilizzando il fondo della sala dove sono a disposizione questi dispositivi. Il professor David Barrow è già stato ospite di Festa della Scienza e della Filosofia 2 anni fa, dove ha tenuto una conferenza plenaria come questa e una lezione mattutina agli studenti. Il tema che è stato utilizzato la volta precedente riguardava l'evoluzione dell'universo. Come vedete dal titolo della conferenza che è alle mie spalle, anche in questo caso il nucleo portante dell'intervento riguarderà cosa vogliamo conoscere riguardo all'universo. Alcune brevi note biografiche per chi non conoscesse il professor Barrow. Si tratta di un professore che in questo momento sta insegnando nell'Università di Cambridge, è un professore di matematica, però è riduttivo ridurre le sue competenze perché in realtà è contemporaneamente un astrofisico, ha fatto un postdottorato nell'Università della California a Berkeley, è contemporaneamente un accreditatissimo cosmologo ed è infatti questo l'argomento oggetto della sua lettura e spende moltissima parte anche delle sue energie per divulgare quelle che sono, diciamo, le sue ampie competenze. Ha più di 500 pubblicazioni di carattere scientifico, ha scritto moltissimi libri tradotti in svariate lingue, è uscito credo quest'anno nel 2016 un testo divulgativo che ha come nucleo portante, leggo il titolo, 100 cose che non sapevi di non sapere sulla matematica e le arti. Stamattina chi di voi ha avuto il piacere, il professore ha tenuto una conferenza per le scuole e il tema appunto del suo intervento era le connessioni che ci sono tra la matematica e le arti, che è uno dei tanti interessi del professore, che è appunto quello di individuare dei collegamenti numerici a livello anche della realtà osservabile. Ha anche altri interessi particolari perché scrive anche a livello amatoriale come autore di teatro, quindi direi una personalità ampiamente poliedrica. Non vorrei farvi perdere ulteriormente del tempo e credo che possiamo dare la parola al professore. Vi ringrazio.
Years ago, in 1915, Albert Einstein developed a remarkable new theory of gravitation. It was called the general theory of relativity, and for the first time it provided astronomers and physicists with a theory based on mathematics which could describe entire universes. Before this time, cosmology was rather like a branch of art history. You could imagine any type of universe you wished. There was no way of predicting or testing a theory of the entire universe. But Einstein's theory provided a set of equations, every solution of which described a possible universe. And so you could set about testing the predictions of this theory using astronomy to decide which was the universe that best described the one that we see and inhabit. It was soon realized that most solutions of Einstein's equations have a property that they describe expanding universes. At first, Einstein didn't wish to introduce this feature into his description of the universe and tried to avoid it. But it was soon realized when astronomers made observations that confirmed that the universe was expanding, that expanding universes were the right types of description for our universe. So I want to ask a series of questions about the expansion of the universe so that we can get clear what the idea is. It sounds a simple idea, but on second thought, it's not necessarily so obvious. So if we say that the universe is expanding, what do I mean? Are you expanding? Is Foligno expanding? Is the Earth expanding? In all cases, no. Not even our solar system is expanding. Our galaxy is not expanding. Our local group of galaxies is not expanding. All these structures are held together by other forces that are stronger than the effect of the cosmic expansion over their scale. To find the objects that take part in the expansion of the universe, that act as markers and tracers of the expansion, we have to go out to great clusters of galaxies containing hundreds or even thousands of galaxies. These are the structures in the universe that trace the expansion. Everything smaller does not expand. It's rather like having a great lump of dough in the bakery and putting raisins in the dough and then placing the dough in the oven. The raisins do not expand, but the dough does. So the dough gets larger and the raisins move away from each other. The raisins are like the clusters of galaxies, and the dough is like the space in between. Many people think of this expansion as if it is an explosion. And their first question is, what is the universe expanding into? Or does that mean that the universe started at one point and expanded outwards? In both cases, the picture is not really correct. The expansion of the universe is not an explosion. The universe is not expanding into anything because it is everything that there is. And in fact, there is no center and there is no edge to the expansion. So how can this be? Let's look at one simple artistic image of this for the case where the universe is infinite in size. So in this case, there obviously is no edge. There is no outside of the universe because it's infinite in extent. In this picture by Escher, he has given a drawing of a never-ending lattice of girders. If you stand on this one and you look around you, you see the same picture on the average than if you stand on this one and look around you. So there is no center to this universe. It is as though every place is the center. Every place, here, 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 or here, or here. They all act as though they are a center. Suppose you increase the temperature in this universe and these metal girders all expanded in length and size. Then if you located yourself here, you would see all the other ones expanding away from you as though you were at the center. But you would see the same thing if you located yourself here. So there is no single center, and there is no edge. This is all very well if the universe is infinite, but what about if it's finite? At first, if we just had a two-dimensional universe like this piece of paper, it seems that it would have to have an edge, and it would have to have a center if it's finite. How could it be otherwise? Well, Einstein's theory taught us that space is not fixed like the floor in this room. It is not like a stage on which particles and galaxies and stars move around, but it is more like a rubber sheet, like a trampoline. And as mass and energy moves around in the universe, it alters the shape and the curvature and the geometry of space. And this is the basic effect of gravitation. So space can be finite if it is curved. So instead of a two-dimensional universe that's a flat surface like this page, we should imagine one that is the surface of a ball, like in this case. So this is a finite surface. You only need a finite amount of paint to paint it. And if you were walking around on this surface, you would never run into an edge. So it has no boundary, but it is finite. It is not like the page, which is finite but does have a boundary. If we inflate this balloon, it gets larger and larger. If we were to locate ourselves at one of these imaginary galaxies and look on the surface, we see all the other galaxies expanding away from us as though we are at the center of an expansion. And we see the same thing if we locate ourselves here, or here, or here. So this is just the situation as in the infinite universe. There is no center of the expansion on the surface of the balloon, and there is no edge. So in both situations, you can have an expanding universe that has no center and has no edge. Throughout the 20th century, astronomers built up a picture of the history of the universe that we would expect to ensue if it's expanding. What the expansion does for you is to create different conditions at different times during the history of the universe. And this is some measure of the size or the amount of expansion that's occurred. And this is the age of the expansion in billions of years. And here is the trajectory that maps out the expansion size against time. We live somewhere here, about 13.7, let's say 14 billion years after the apparent beginning of the expansion. So we don't know if that's the beginning of the universe, but it's the beginning of the expansion. If we were to run the clock backwards to when the universe is 1,000 times more contracted than today, the temperature will be 1,000 times greater than today. Today, the temperature is about 3 degrees above absolute zero. It's very, very low. But back here, when it's 250,000 years old, the temperature would be 3,000 degrees. And there could be no atoms, no molecules, no planets, no stars, no galaxies. Just simple nuclei, electrons, elementary particles like neutrinos, and photons of light. So the universe is a very simple place when it is just about 1 million years old. It then gradually ages and cools off so that simple structures can form. At first atoms, then molecules. Eventually, parts of the expansion, which are going a little more slowly than others, will capture more material. They will separate off from the expansion and form galaxies and clusters of galaxies. And within them, stars will form, and then planets around stars, and by some complicated process we don't understand in detail, life in various simple and complex forms, like our own, evolved at least on the surface of one planet. We now have discovered more than 1,000 planets around other stars. So we know planet formation is a common process that happens all over the part of the universe that we have seen. In the future, the long-range forecast is rather bleak. The stars will eventually consume all their nuclear fuel, and they will die in various ways. The small ones will form massive stars called white dwarfs, about the size of the Earth, but 1 million times more massive, and they will just cool down forever. More massive stars, more massive than 1.4 times the mass of the Sun, up to about 3 times the mass of the Sun, will form neutron stars, which the last speaker described as the basis of pulsars we see today. And if they are more massive than 3 times the mass of our Sun, then they will form black holes of the sort that gravitational wave astronomers observed directly in the last 6 months for the first time, emitting gravitational waves. But in the long term, all the stars will cool and all the stars will die. And the universe looks like a great cemetery of past stars and former planets. So there is a period of cosmic history after the stars form, but before the stars die, when it is possible to evolve and sustain life of the sort that we are. So what we see of the universe is biased by the fact that we have to exist in this interval of cosmic history after the stars have formed, but before they die. So let's have a look at some of the consequences of that. We can ask some simple questions about the universe. I said today it's 14 billion years old, roughly, 13.7, the best estimate. So why is the universe so old? Should we be surprised that the universe is so old? Well, if we think of ourselves, we are pieces of complicated biochemistry. We rely almost completely upon very unusual chemical properties of the element carbon. And many other elements like nitrogen and oxygen. If you are an artificial intelligence, you will be relying on the properties of silicon and silicon physics. But all these elements don't just come into the universe ready-made. They don't come from the beginning of the universe. They're made in the stars. And when the stars die, these elements are dispersed around the universe. And they find their way into rocks and debris and planets and ultimately into you and me. The most interesting sequence of nuclear reactions at the end of a life of a star before it explodes is for 2 helium nuclei to combine to make beryllium. And for beryllium to capture another helium nucleus, an alpha particle as we call it, to make carbon. And then for carbon, say, to capture another helium, and that makes oxygen. This reaction goes remarkably rapidly because of a coincidence amongst the energy levels of the carbon nucleus, and this one does not go so fast because of another coincidence about the energy levels. But all the carbon nuclei in your bodies have all come from this process in the stars. And they may even have gone through a star more than once. So this is the origin of the old sort of pop song line that you are stardust, that we are made of the debris of the stars. And this sequence of nuclear reactions takes billions of years of time to complete. So we should not be surprised to find that we are living in a universe that's many billions of years old. A universe that was significantly younger than this could not contain the building blocks of chemical and biochemical complexity. If we ask a second question, find that it's closely linked. Should we be surprised to find the universe so big? So why is the universe so big? Well, we've seen just now the universe is expanding. It has to be billions of years old to have enough time to make the building blocks of biological complexity and life. And so it must also be big. It must be billions of light years in extent because of the time that's needed to make the complexity that constitutes ourselves. You might have imagined that we could have a universe the size of the Milky Way galaxy. That would contain 100 billion stars, like the Sun. But such a universe, although vast in extent, would only be about a month old. So there's hardly enough time to pay off your credit card bill, let alone evolve complexity and biochemistry and life. So these unusual features of the universe, its great age and its great size, are closely connected with the fact of our own existence. A third odd feature of the universe is that it's almost empty. To a first approximation, there is nothing in the universe. The average density of material in the universe, if we were to take every atom in the universe and space it out evenly throughout the universe of space, there would be about one atom in every cubic meter of space. There is no laboratory on Earth that could make a vacuum that is as empty as that. So in practice, we don't just have a universe that has equally spaced atoms in it, but the atoms are gathered up. For example, if you gather one atom of a cubic meter into objects the size of planets, it would correspond to running into one planet like the Earth every 10 light years. If you gathered them into stars like the Sun, it would correspond to running into one star every 1,000 light years. If you gathered them into galaxies like the Milky Way, each containing 100 billion stars, you would have to go 10 million light years before you reach the next galaxy. So you begin to appreciate the effect of this low density on the distances between stars and planets. You shouldn't be surprised that it is so far to the next star, and that extraterrestrials are such a long way away, if they exist at all. This is a consequence of the low density of material in the universe, and that is a consequence of the large age and the large amount of expansion, which has diluted the density as it's expanded for billions of years. So the low density is another byproduct of the required age of the universe to make elements like carbon. Another consequence of this large amount of expansion is that the universe is cool. The temperature is extremely low. So I said earlier it's about 3 degrees above absolute zero. And this again is a consequence of the huge amount of time and expansion that has taken place. The temperature falls as the expansion continues. If you have a rubber ball full of gas and you expand its size, it will get cooler. If you compress it, the temperature will rise. The temperature is just the average speed of the particles in the gas. But there is another curious consequence of this. If we look at this photograph here in the background, this is the famous Hubble Deep Field. Every blob of light that you can see in this picture is a galaxy containing 100 billion stars. And this is just a tiny piece of the sky. It's about the size of my thumbnail at arm's length on the sky. So there are trillions upon trillions of stars in this picture. But there is a mystery about this picture, like all other astronomical pictures. And that is not the stars and the galaxies which are shining, but the dark spaces in between. So 300 years ago, Edmund Halley, who discovered and predicted the return of the famous Halley's Comet, first asked an unusual question. And the question was, why is the sky dark at night? Well, at first you might think he just needs to get out more? It's an odd question. But if you look at his reasoning, you see why he asked this unusual question. Suppose you look into a forest, trees everywhere. Your line of sight everywhere ends on the trunk of a tree. So that as you look across this picture, everywhere you just see tree trunks. And you don't see very far. So Halley was interested in whether the universe might be infinite. Could we have an infinite number of stars or just a finite number of stars? And he realized that if you looked out into the universe, he asked, why doesn't the same thing happen with the stars as happens with the trees? So why doesn't your line of sight everywhere end on a star, so that the whole of the sky looks like the surface of the sun all the time? And it wasn't until the 20th century and the discovery of the expanding universe that anyone could answer this question. You see, the very low density of material in the universe means that there just isn't enough energy in the universe to illuminate the sky. If we were to turn all the stars and matter into radiation today, just like that, all that would happen is that the temperature of the universe would rise from 3 degrees above absolute zero to about 16 degrees above absolute zero, and we wouldn't notice anything peculiar at all. So this huge amount of expansion that's necessary to produce the building blocks of life has lowered the temperature and the density of material to such an extent that the sky has to be dark today. But there was a time in the past when the universe was 1 million years old or so. You remember when you were 1,000 times more contracted, then the sky was bright all the time. The temperature of the sky would be thousands of degrees. So there was a time when the sky was always bright, but it was at a time when there could be no atoms in the universe, there could be no life, and no astronomers. So these unusual features of the universe, we could summarize that if you want your universe to support the existence, development of life, then it needs to have some peculiar properties. It's got to be almost empty, it's got to be big, it's got to be old, it's got to be dark, and it's got to be cold. So these are properties that philosophers of the 19th century and the early 20th century would have regarded and did regard as being somehow opposed to the nature of life and opposed to the picture of the universe as being in any way hospitable to the development of life. But modern astronomy has turned that view on its head, and we see now that these are necessary features of any universe that is going to develop and support life at all. And they all flow from the requirement that the universe has to be old enough to produce the building blocks of complexity and chemistry. Well, from the 1960s onwards, we've developed a very robust and detailed picture of the expansion of the universe. We've talked so far about size against time, universes that expand and keep on expanding. But there can be other sorts of universe that expand more slowly, and eventually the gravitational pull of their constituents reverse the expansion back to collapse and to a big crunch in the future. And then there are galaxies that run away faster and faster forever, and there is one type of universe in between where the two features just exactly balance. And we call this the critical universe. Our universe is within 1% or 2% of that critical divide. And this was always a puzzle to cosmologists, because you can see just from this picture that if you are not exactly on a critical divide, you tend to peel away down here or run away up there. So we say that the critical expansion is unstable. If you perturb it very slightly, it will become more like this or more like that. So if after 14 billion years you are still close to the critical divide, it means that the starting rate of expansion must have been very, very finely tuned. In fact, tuned with an accuracy of 1 part in 10, followed by 32 zeros. So this was always a puzzle. The great discovery of the 1960s, about 50 years ago, by cosmologists was to discover the heat radiation left over from this hot, dramatic, early stage of the universe. So in 1965, this was discovered, and in the decades that followed, it was systematically observed from the Earth by radio astronomers and then by satellites. So this picture shows the intensity of this radiation against its frequency. The solid lines are to guide what the shape will be of a spectrum of pure heat radiation. And the circles here are the observations from space of this radiation. These circles are not representing the uncertainty in these observations. The uncertainties of the measurements are 500 times smaller than the thinnest line that could be drawn on this picture. So what these observations show is that the universe is full of heat radiation with a perfect so-called black body spectrum, the most perfect example of heat radiation ever discovered in the universe. And the temperature is about 2.73 degrees Kelvin, above absolute zero. This radiation was predicted in a general way back in 1948, and it was expected then to have a temperature of about 5 degrees above absolute zero. So this is a pretty good result, a pretty good agreement with what some people had expected back in 1948. And we can study and map the properties of this radiation in all sorts of interesting ways. And one of the features of the radiation is that the temperature is the same in every direction of the universe to an accuracy of a part in 100,000. So this tells us the universe is expanding at the same rate in every direction, like an expanding sphere. It's not like an expanding ellipsoid or a cube. So its properties in that direction are the same as they are in that direction, to an accuracy of a part in 100,000. And also, the smoothness of this radiation tells us that the universe is rather smooth in space everywhere, to an accuracy of about 1 part in 100,000. So there are not huge variations in the density of material from one place and one direction to another. It is very smooth and even, like the surface of a mill pond, rather than some huge raging ocean of waves. So by 1980, there were 3 features of the universe that were puzzling, which we didn't have an explanation for, but which we could observe. One was that it was expanding very close to this critical speed. And the next one was the expansion had the same rate in every direction. We say it's isotropic. And the third is that the graininess, the non-uniformity, is very small. And it has a very particular value, about 1 part in 100,000. This is an important number, and we would like to understand why it's this number. If it was 1 part in a million, so this is a 6, the graininess would be too small for any galaxies and stars to exist in the universe. If it was 1 part in 10 to the 4, 1 part in 10,000, so it's 10 times stronger, all the galaxies and stars would have formed extremely dense objects very early on, and again there would be no life-supporting environments. So this is a nice number for us, and we would like to understand where does it come from. Well, in 1980 and 1981, a new theory of the universe and how it behaved in the very earliest stages was proposed by Alan Guth in the US. And this answered all these questions at one go by introducing one simple idea. And it made some predictions which allowed you to test the idea. So this is the standard picture of the early history of the universe today. And so I want to describe this in a simple way. And by the early history, we mean this tiny fraction of a second here, 10 to the minus 35. Here's our picture, size against time. In the pictures I've shown you so far, this trajectory always curved over in that direction. What that's telling you is that the universe is decelerating. So once it starts expanding, gravity decelerates it by attracting between all the material within it. But Guth's proposal was that there was a very short period near the beginning of the expansion where it accelerated. So it changed gear and accelerated. There were good reasons to make that suggestion because at that time, theories of elementary particle physics had discovered that there was always a prediction that a certain type of elementary particle, a certain type of energy field, was likely to exist in these new theories. And it has exactly this effect on the expansion if it's present in the early stages of the universe. It's a type of energy field or particle like the Higgs boson, which was discovered just a few years ago. The reason that this interlude comes to an end is because it's expected that these particles are unstable. So they drive the acceleration here, but then they gradually decay and turn into ordinary types of radiation and other particles that don't have this anti-gravitating effect. The effect of this you can see from the picture. It makes the universe become much more expanded by this time, much bigger than it would have done if it had followed this trajectory and it hadn't accelerated. What this does is to drive the expansion fantastically close to the critical divide, so that even by the present, it's still too close to the critical divide to tell on which side it will ultimately expand. The second unusual feature is the surge of accelerated expansion. Regardless of what the expansion was back here at different rates in different directions, every direction will be expanded and accelerated to expand at the same rate. So at the end of this phase, the expansion will be completely isotropic and spherically symmetric to very, very high precision, regardless of what it was like before. So those two puzzling features of the universe are naturally explained by this tiny period, just 10 to the minus 35 to 10 to the minus 33 of a second, is enough to explain these observed features. But then somebody noticed something else about this type of cosmology. Suppose that we look at the last picture in a different way. We're located here, and we ask, how far could we see with a perfect telescope? Well, we said the expansion had been going on for about 14 billion years. So we'd expect to be able to see 14 billion light years. In fact, you can see a bit further than that because of the expansion. But that's our horizon. Light has not had time to reach us from farther away as yet. So this defines what we call the visible universe today. So the part of it that we've had time to see. And we could take that part, or a little bit bigger, and run it backwards, and to say how small was it at some time in the distant past. And what this acceleration enables us to do is to expand the whole of the visible universe from a region that is so small that light signals can travel from one side of it to the other. If you don't have this accelerated expansion, that is not possible, because our universe emerges from a region which is far too big for that to happen. So this explains two things. First of all, why on average the universe is so similar in structure from one place to another. Because it's all a reflection of the fact that it's an expanded image of a region that's so small that it's kept coordinated and smoothed and correlated by light signals and other physical processes. But then it was soon realized in the early 1980s that there was something extra to this picture. This little coordinated region that will eventually encompass the whole of our visible universe cannot be perfectly smooth. There must always be some statistical quantum fluctuations within it, and we can calculate what they should be. And what will happen to them is that they will be expanded and stretched, and they will be reflected in the structure of the universe today and in the temperature of the radiation around the sky. So we might be able to predict how the temperature of the universe and its radiation should vary around the sky as a result of these quantum fluctuations in its earliest moments. So this allows you to test whether this process of inflation, as it's called, ever occurred. So this is an exciting prospect, and it's been the motivation for a succession of space missions, the first two by NASA, and the most recent, the so-called Planck mission by the European Space Agency, with many, many scientists from European countries, Italy, United Kingdom, Spain, Holland, Germany, and others, playing a key role in planning the satellite mission, controlling the satellite from France and from Holland, and then analyzing the data involved. And this is one picture of the final data. This is a temperature map of the radiation around the sky. You could think of us as sort of living in the center here, and we're looking up at all of the sky around us in the universe. And the places which are red, end of the spectrum, are a tiny fraction of a degree above the average temperature, and the blue ones are below the average temperature. So this is a temperature map of the universe. The changes in color are 100,000ths of a degree. So this is a very, very fine resolution map of the universe. And what we do with this, you can do many statistical things, but a simple thing is to take the temperature in one direction and then measure the temperature in another direction, say 10 degrees away or 5 degrees away, measure the difference. Measure the differences at all 5 degree separations over the entire sky and take the average. And do this for all separations and plot it on a graph like this. So here are the color differences, the temperature differences in millionths of a degree squared. Here, the variance, if you're a statistician, roughly. And here's the angular scale that you were making the comparisons on. And this green solid curve is the prediction of what you should see if this surge of accelerated expansion occurred. And it has a distinctive feature with this large peak here. The location of that peak tells you how far you are away from that critical expansion rate. So by measuring the location of this peak here, you can determine how far away we are from the critical expansion speed. And then there are these other peaks, and everything damps out on smaller and smaller and smaller scales. So you can see that what you have is a series of shapes like this, and you can move them up and down to find the best fitting configuration, and this is evidently a very, very good fit. If the acceleration had never occurred, you would be looking at a picture which had not got this peak at all. It would just be largely flat across here. So we have direct observational evidence that this surge of inflation occurred very early in the history of the universe. The other dramatic thing is that the relative sizes of these peaks, their distances apart and so forth, contain all sorts of other pieces of information about the structure of the universe. And I'll just show you two little movies which illustrate this. So remember the general shape here with the peak and the secondary peaks here. So here are two theoretical predictions of what that last picture should look like if you change some things about the universe that you don't know precisely. So this is how much matter is there in the universe which is luminous and visible. So it's made out of atoms and molecules. And you can see as you change the fraction here from low 2% up to this looks like 6%, you can see the effect. It changes these peaks very dramatically. So you have a diagnostic to determine the best fit of your picture and to determine the best estimate for the amount of luminous material in the universe. You could do the same thing for the dark matter, the non-luminous material, which affects the picture in a different way. And you can see here, as you change that fraction up between these values here, from low to high, again you alter the height of this peak dramatically. And the relative height compared with the second and the third peaks also changes. So this is why cosmologists are so interested and have spent so much of their resources on mapping this radiation. Potentially, it can give extremely accurate determinations of all sorts of other properties of the universe, because this picture is so sensitive to these other properties. Well, this is a rather sort of standard picture now of the structure of the universe and this theory of inflation. But back in the 1980s, after it was proposed, cosmologists realized that there were two other rather more dramatic, philosophically peculiar consequences of this theory. And one I'll call chaotic inflation, and it should persuade you that the geography of the universe is a much more complicated subject than geography was when you were at school. So we had focused on some little patch which is going to accelerate and dramatically, and it ends up enclosing the whole of our visible universe today. We know that that better undergo enough inflation for there to be enough time for the carbon to form and the other elements, for the reasons we explained early on. But our universe may be infinite, so there'll be all sorts of other regions, and they may undergo different amounts of inflation. It's rather like the heating of a great foam of bubbles. And we're in a bubble that keeps on expanding for 14 billion years at least. But beyond our visible horizon, there will be other regions, which are the expanded images of other small regions. So this theory predicts that although locally our universe should be very smooth and coordinated, if we could go far enough beyond our visible horizon, we should expect the universe to become completely different, to have a structure that reflects the inflation of other regions that may have been completely different. And in some versions of this theory, what is different in these other regions is not just the density and the temperature and the expansion, but some features of the laws of physics, which are determined randomly in these different parts of the universe back there. So this is the first time there has been a positive prediction that we should expect the universe to be very, very different in space if you go far enough beyond our visible horizon. Well, as if this wasn't bad enough, it was then realized that this process can also continue in time. and that the history of the universe is more complicated than it used to be. So here we are in one of these little bubbles that starts off very small, it inflates and becomes our whole visible universe. But it's realized also that once this happens, it tends to create within the inflated region conditions for other little parts of itself to undergo further inflation. And they in turn will create conditions for further inflation of parts of themselves. And the whole process is self-reproducing, and it never ends. It may also never have had a beginning. So suddenly we see ourselves as one inflated region in the midst of a historic process that may have been going on forever. And if you say, did our universe have a beginning? It did have a beginning. There was a start to the inflationary process for our patch here. We don't know the nature of that beginning, but whether the entire process of internal inflation, sometimes known as the multiverse, whether this had a beginning, we don't know. It doesn't seem to need to have a beginning, even though each member of the multiverse does have a beginning. So the history of the universe is now a rather more complicated and peculiar process. And the number of these regions which are inflating and continuing is absolutely enormous. 10 to the power 10 to the 77. So each one of these regions produces a huge number of additional regions, and the process continues branching forever. Well, this is sort of the origin of reporting that you see nowadays about the multiverse, the idea of other universes, and so on. I like to think of it more as there being one universe, but within it, in different places, the structure is very, very different. So it's like a non-uniform and irregular universe. Some parts are expanding, some parts could be contracting. Some parts could be extremely irregular, and others, like our own part, extremely regular and smooth. Well, that's all I want to say about the past of the universe. Let's finish by saying something about the future. So is the universe going to expand forever? Or will it eventually run into a big crunch? Well, in some ways, this is not something that will bother our descendants, because the solar system has a lifetime which is much shorter than anything that's going to happen to the universe as a whole. Our sun formed about 4.6 billion years ago. About the same time, a bit later, the Earth formed. It's a sobering thought that you can go and walk around in Scandinavia or even the north of Scotland, and you can pick up a rock or a stone on the ground that is nearly 4 billion years old. So you can just find things which are 4 billion years old. Our whole universe, our whole solar system is not very much older than one of those things. What's happening, though, is that the sun is gradually consuming its hydrogen, and eventually, after another 5.5 billion years, it will undergo an energy crisis, and it will expand dramatically to form what's called a red giant. And this will vaporize the planets, the inner planets of the solar system. So our descendants better have moved somewhere else or tunneled deep, deep underground. Then the red giant phase will implode to form a white dwarf, the size of the Earth, 1 million times denser. We see many of these objects in the universe. Here's a Hubble Space Telescope picture of that event. It's more complicated. There are 2 rings being blown off by the explosion as the center implodes. Maybe there are 2 stars in this system, or there is a magnetic field or something more complicated that creates 2 explosions rather than 1. After that, things just keep cooling down forever. And all stars will follow similar sorts of fate, either white dwarfs, neutron stars, or black holes. So the time scale on which this is happening, 10 billion years from the start, is much shorter than the time scale on which the whole expansion of the universe is going to do dramatic things. But in 1999, a remarkable discovery was made as a result of new technologies and new ideas in astronomy. That for the first time we were able to observe exploding stars on the edge of the visible universe and know what their intrinsic brightness was, so that their apparent brightness could tell us how far away they were. And what they told us was the expansion of the universe is actually speeding up if we look far enough away. It's accelerating, it's inflating, if you like, today. So our picture of the size against time of the expanding universe, inflation was way beginning. As we go forward, a million years, radiation cools off. Then after a few billion years, the expansion changes gear and starts to accelerate again. So today the universe is accelerating, just like it was in the distant past for a brief moment. But this acceleration started when the universe was about 3/4, 75% of its present extent. So this is very mysterious. We have no idea why this started at that time. We can give very accurate descriptions of the acceleration, but it's a big mystery to physicists and astronomers as to why this phenomenon should suddenly occur when the universe is about 3/4 of its present size. And when it occurs is a rather important thing. If it started just very slightly earlier, then the universe would have started accelerating so soon that there wouldn't be any galaxies and stars. Material would be pulled apart too quickly to condense to form galaxies and stars. And there wouldn't be any astronomers. We don't seem to care if it happened later. It doesn't seem to have any effect. But we can't understand why it occurred at this time that it did. Sometimes today the effect, the energy in the universe that's creating this acceleration is known as dark energy. So what do we know about it? We know it is anti-gravitating. It has a negative pressure, like the same material that gives rise to inflation early on. But we don't know its exact identity. We can't match it up to some type of elementary particle in some other theory of elementary particle physics. That's a challenge for the future. How much of this energy is there around? So the Planck mission ended up with this type of picture for the energy budget of the universe today. So 68% roughly of the energy in the whole universe is in the form of this dark energy, which is driving the expansion, accelerating the expansion. And it shows up in the undulations of that microwave radiation fluctuation picture as well. Over here we have everything else. Just less than 5% is ordinary material that you and I are made of, that shines in the dark, makes stars and planets. So this is atoms, molecules, hydrogen, protons, things that we understand. The way that material moves around tells us that it is feeling the gravitational field of another type of dark material. So this is material that hasn't got dense enough for nuclear reactions to turn stars on and to shine in the dark. This material we call dark matter, and the prime candidate for this material are new elementary particles, which are neutrino-like, and so interact very weakly. At this moment, in every cubic centimeter of this room, there are 400 of these particles flying past, with a speed of 250 kilometers per second. Millions of them are going through your head at this moment, but they interact so weakly that you don't feel any effects. And that's why it's so hard to detect them. The next great challenge for the Large Hadron Collider at CERN in the next year or so is to detect these elementary particles. So to raise energies sufficiently that you can make them for the first time on Earth in an experiment. They're about perhaps 30 or 50 times heavier than a hydrogen atom. And previously, we've not been able to generate enough energy to produce them artificially. But the great quest for the Large Hadron Collider at CERN now is to make those particles, measure their masses, and see if they exactly fit the requirements to produce this amount of dark matter. So most cosmologists believe that this problem will be solved in the not too distant future. On the timescale of a few years, we will identify that type of matter. But this problem is more profound. We don't have any solutions to this problem. We don't have a natural explanation as to why the universe started accelerating in the recent past. The fact that it is accelerating tells us that the long-term fate of the universe is to expand forever. It's not in one of these trajectories that will one day reverse into contraction and head towards a big crunch. That it seems to be destined to expand forever. But that expansion has another very peculiar property, that if you're in a universe that's accelerating today, then it's like being inside a black hole, that eventually light will not be able to keep up with the accelerated expansion, and there will be an absolutely fixed limit beyond which we cannot see. Eventually, all the local galaxies that we observe today will pass out through that boundary, and astronomers in the far, far future will not have a way to determine that the universe is expanding. They won't be able to see all the external galaxies that we see today. So we saw earlier on that we live in a period where life is possible after the stars have formed but before they die. We also live in another period of cosmic history where it is possible to study and understand the large-scale structure of the universe. In billions of years' time, this will not be possible. The only way to study the expansion and the history of the universe will be to read about it in old books. You won't be able to determine the universe is expanding. There will be a limit beyond which you cannot see, and gradually all the galaxies will pass beyond that limit. So this is a summary, really, of that peculiar situation, that there are many things that we can mean by the universe. You can mean the part of the universe that we've seen so far with our telescopes. But there is also what we call the visible universe, that 14 billion light years away, that with a perfect telescope we could see. But the acceleration of the universe means that even in an infinite future, there is a boundary, there is another horizon beyond which we can never see. So our visibility is constrained. Yet beyond that, there will be lots and lots of universe that we could never see. And perhaps if our universe is just one of those regions in this never-ending multiverse, we are embedded within some huge multiverse. So just as Copernicus showed that we are not the center of the solar system, even our universe is not at the center of the universe. So I hope this is not too sobering a thought for Friday evening. And I leave you with a more homely picture of the Milky Way with the Andromeda Galaxy superimposed. Thank you.
Allora, ringraziamo il professor Barrow per la finestra che ci ha aperto su queste interessanti sfide. Se ci sono da parte del pubblico delle domande, prego.
You will need, are they going to ask questions or not? No.
I ask, but probably they are afraid
Yeah.
because they must speak in English.
Yes.
Probably.
I was going to say, if they ask in Italian, you could just translate it to us.
Vi incoraggiamo a fare domande, professore, a piacere se qualcuno di voi chiede qualcosa. Grazie. Allora, cerchiamo il microfono di sala per cortesia, arriva subito, grazie.
Okay. First of all, thank you, Professor, for being here in Foligno once again. And you said that the inflation is on a provoking this inflation. So probably